So today is our second lecture in this chapter on heat exchangers. We covered all the way through the log mean temperature difference method. Today we'll be able to get into the effectiveness-NTU method, although I'm going to spend some more time here in the log mean temperature difference method. One thing is there's really two big methods to analyze heat exchangers, not 3 or 4 or 5, just two. The log mean temperature difference and then the effectiveness-NTU. This one is abstract. Maybe it's hard to wrap your head around when you're first introduced to it, but once you get to know and become familiar with the effectiveness-NTU method, that's the preferred method because basically it avoids the need for iteration. So with the log mean temperature difference, sometimes you're stuck needing to iterate. Where here they basically continued to work with the mathematics, manipulate the equations, and package it such that you can go this direction or that direction, and often, not always, but often avoid iteration. So let's review here for the log mean temperature difference for counterflow concentric tube heat exchanger. Just in summary, divide it like this, maybe call this the hot side, maybe call that the cold side. Maybe we have fluid coming in, temperature hot in, temperature hot out. Then we have the temperature cold in and the temperature cold out. There's three big equations and you can't forget them. You use them all the time. Two of them are straight from thermodynamics 1, Thermo 1. It's an energy balance from the perspective of the hot fluid. It says the rate at which the heat is coming out in kilowatts or watts, the rate of heat transfer out of the hot fluid is equal to the mass flow rate of the hot fluid, the specific heat out of the hot fluid, times, this is for hot, times the temperature hot in minus temperature hot out. Sometimes they'll just put this cap C hot, temperature hot in minus temperature hot out. What is this cap C? Heat capacity rate for the hot fluid. The other one is an energy balance from the perspective of the cold fluid. The same rate of heat transfer, Q is the same in both of those equations, so many watts, so many kilowatts, is equal to the heat capacity rate of the cold fluid times the temperature cold out minus temperature cold in. The last one, which is our rate equation from heat transfer, understanding the mechanics by which heat is transferred, is Q is equal to UA times the log mean temperature difference. Sometimes I'll write it like that. Sometimes I'll put delta T LM. It's the same. Log mean temperature difference. LMTD or delta T with LM. And then what is this log mean temperature difference? Well, think about getting a temperature difference on this end. Call it delta T1. It's always going to be the hotter minus the cooler or lower temperature. So temperature hot in minus temperature cold out. And then delta T on the other end, delta T2 is equal to temperature hot out minus temperature cold in. And the log mean temperature difference is the temperature difference one end minus temperature difference the second end divided by the natural log temperature difference 1 over temperature difference 2. We spent some time talking about that last time. I want to spend just a little more time talking about it again. This was the derivation. We covered that last time. So somebody says delta T1 is 30 degrees C and delta T2 is 50 degrees C, and you don't have a calculator, what would you guess the log mean temperature difference to be? Around 40. You take those numbers, stick it into your calculator, 39.15. That guess is pretty insightful. It's essentially a good average temperature through the, or temperature difference, through the heat exchanger. All right, somebody says the delta T1 is 29.5 and 30.5. What do you think the log mean temperature difference is for this one? 30, 29.997. Okay, it's really close to 30. And then the classic, some student with a calculator, hey, delta T1 is 30. delta T2 is 30. They run it, and what do they find? Divide by 0 on their calculator. But what is the log mean temperature difference when it's 30 on one side and 30 on the other side? It's 30. It's 30. And remember from calculus, L'Hopital's rule, and we covered that last time. True? So that you use that knowledge from calculus to help convince you when delta T1 is equal to delta T2 that the log mean temperature difference is that temperature difference. All right. I take a plot. I plot the hot fluid profile through this concentric tube heat exchanger. I plot the cold fluid temperature profile through that. And then I do it for 3 cases. Here's hot, here's cold, here's hot, right? And I say, which case of these 3 has the largest log mean temperature difference? Case A, B, or C? I'm trying to help you build insight into the problem. One of these I think you can look at and say, hey, from the givens, I can tell what the log mean, without touching my calculator, I can tell what the log mean temperature difference is. Is that for case A, B, or C? C. The log mean temperature difference for case C is a spot on 30 degrees C. It's like the temperature difference on this end, it's temperature difference throughout. All right. Let's say you want to guess this one. Give me a guess for the log mean temperature difference for this one. You think it's above 30? Do you think it's below 5? No. Do you think it's what? What do you think it might be? I'm sorry?
14, 15.
All right, we're going to take 14. Okay? Let's take a look at this one. Log mean temperature difference for this case. It's 15 on one side, 30 on the other. What do you think? 23? Building some insight. Jump on your calculator and you get more digits on all of those. But if somebody said, this one's around 23, this is 14, this is 30, I'm going to re-ask the question. So here I just ran these numbers to get more digits. I think if somebody ran them, they probably confirm those, right? I ran those on my calculator. So anyway, let's grade it. Congratulations. Some people know that 30 is bigger than 23, and that's also bigger than, but let's go back now when we first asked the question. So yeah, there you go. Okay. So C is the best answer. All right. I'm trying to help you build insight. Here's another question. You have the same concentric tube heat exchanger, and you have the profile of the hot fluid, and you have the profile of the cold fluid. But I don't know if they're counterflow. I don't know if they're parallel flow. I just don't know. Can you tell which one is it counterflow, parallel flow, or really I don't know? Let's focus on the hot fluid. Let's assume the direction of the flow of the hot fluid is that direction. And let's, in our mind, take a little chunk of hot fluid. That must be the end, and it moves from here to here to here to here. It's moving in that direction. As it moves in that direction, does the temperature of that chunk of fluid get warmer? Does it get hotter? Or does it go down and get cooler? Does that make sense that that probably is the direction of flow then for the hot fluid, wouldn't it be? Yeah, that's the direction of the hot. Let's do the same thing for the cold fluid. Let's assume the cold fluid's going this direction. So we take and conceptually follow a little chunk of fluid as it's going through. Is the cold fluid going to warm up as it's going through, as I've shown? Or is it the profile showing that it's getting colder as I move through the heat exchanger? Does that make sense? I re-ask my question. So, oh boy. Well, we just concluded that this is not the direction of the cold. That has to be the direction of the cold, which means it's counterflow. Counterflow. So congratulations to the 88%. let's go back and see how we did the first time. Congratulations to the 43%. But you get a little insight, and then it can save you when you look at some of your calculations and things don't look right. Okay. You want to play this one? Yes. Was that a counterflow, parallel flow, or I have no idea flow? Good job, right? Not a hard question. If you take a look at this, I want to now talk a little bit about our heat capacity rate. Do you remember cap C? And if you look at this first case right here, would you say the heat capacity rate of the hot fluid is much, much greater than the heat capacity rate of the cold, or the heat capacity rate of the hot about the same as the heat capacity rate of the cold, or the heat capacity rate of the hot fluid much, much less than the heat capacity rate of the cold? Let's vote A, B, or C. All right, so I was hoping this would be more consensus on this. They're about the same, aren't they? And so this brings in this concept. Last time we talked about maybe having maybe this is a direction for the hot fluid, this is a direction for the cold fluid, right? And we talked about if the mass flow rate of the hot fluid went way up, the mass flow rate of the hot fluid went way up, then the heat capacity rate of the hot fluid would be a large, and you wouldn't think that the hot would change much in the way of its temperature change as it goes through. It's like the concept of a thermal reservoir way back in Thermo 1. It's like you can, in a thermal reservoir, you can pull some heat out, you can dump some heat in, but it's not changing the temperature of the thermal reservoir. Like here, the hot fluid stream is so big, it's like a big river. I can pull some heat out, it's not really changing the temperature of that big river gushing of hot fluid through the heat exchanger. The other way that you can do it is you can change the specific heat of the hot fluid, because isn't the product of the two? So far we have focused on the mass flow rate conceptually. This is going to be tricky. It's going to take me 2 or 3 slides, but I want to focus on the specific heat. So can you do me a favor with the friends sitting next to you? What is the specific heat of liquid water at 1 atm? What is the specific heat of water vapor? And then what's the heat of vaporization for water at our favorite pressure, atmospheric pressure, 1 atm? All right, some of you are better at quickly looking it up with your phones or laptops, but what did the water typically come in at? Liquid water. About 4.2, 4.18. Let's just try 4.2. What are the units? Kilojoule per kilogram Kelvin or degrees C. Hey, liquid water, 1 atm. Can I have it below 0 degrees C, or is something special going to happen if I say liquid water at negative 20 degrees C in equilibrium? I'm talking about not some quasi-equilibrium state. Let's just say water in equilibrium, negative 20 degrees C, 1 atm. Is it going to be liquid? No, it's solid. How about 100 degrees C? Let's say somebody says it's 140 degrees C. You have liquid water, 1 atm, 100. It's really, liquid is in here. That's it. That's it. Kind of extremes. 1 atm. Change the pressure. It changes things. All right, what about our water vapor? This one's harder. So it's around 2 kilojoules per kilogram Kelvin. And then the heat of vaporization, it's around 2,000, over 2,000. But what are the units on HFG? It's around 2,300 kilojoules per kilogram Kelvin, or not? No, what's the error? This is no need, it's how much heat per kilogram to change phase, to boil, to vaporize at 100 degrees C at that pressure. All right. So if I could, this is all review, Thermal 1. Somebody says, I have a piston cylinder apparatus. We studied those ad nauseum in Thermal 1 because they gave us a constant pressure. As the system was heated or cooled, the trapped amount of fluid inside or underneath the piston in the cylinder was trapped, and it gave us a constant pressure system. So it's always at this pressure of 1 atm. What is the amount of heat transfer? So this would be in kilojoules for 1 kilogram of water to take it from liquid at a pretty low temperature. Let's say it's a 0 degrees C, but it's like saturated liquid, ready to start freezing, but it's still liquid. All the way up to 200 degrees C at 1 atm, that's superheated vapor. How would you calculate that? I will give you a minute. I'll walk around. Big hint, use specific heats. We just talked about those. What was the value for the liquid water? 4.2. What was the value for the water vapor? 2. And then also use the heat of vaporization around 2300. So let me pick it up from here. So I was looking for an equation where I take the mass. Okay, that's 1 kilogram, or you could have left it off, or put the cap Q over the mass, put it to that side, then you have the lowercase q. But it's the specific heat of the liquid times the temperature change. Well, it's going to go up to 100 degrees C, and then it can't be liquid anymore if I keep adding heat. And it's starting at around 0 degrees C, so there's 100 times C sub P of the liquid, which was 4.2. And then we have the HFG, the heat of vaporization. There's the better number for it, the 4 significant digits, 2257. Okay, close. And then we have the specific heat of the vapor, and we're going to end at 200, but the vapor, needs to be heated, superheated from 100 up. And yes, the water vapor does behave as a good ideal gas and a good constant specific heat at that condition. So this is a pretty good model. So when we run the numbers, it takes about 420. That's a good number to remember. On the next slide, I'm going to use it again. 420 kilojoules per kilogram to take it from pretty much ice, but it's saturated liquid down there at 0 to C, up to saturated liquid at the other end where it's about ready to boil. And then 2257, and then 200 kilojoules. So 77% of the heat is brought in just to change phase. 15% to heat up the liquid, and 7% to heat up the gas, the ideal gas vapor, water vapor. And this is the total. At the end of the day, I had to bring in 2,877 kilojoules for 1 kilogram of water. So what we want to do is we want to somehow start plotting this in a way that makes sense. I'm going to plot it 2 different ways. One is both of these are a little bit abstract, but it's a good review. Go ahead and think about plotting it per Q, how many kilojoules per kilogram come in. And we said, hey, we're going to take it up near 3,000. So here's 3,000, and here is 2,000 and 1,000. 2,000, 1,000, and there's 0. And so I'm going to start bringing it in. And now I'm going to talk about the temperature in degrees C. And what was the highest temperature? 200. What's in the middle? Oh, 100. Where did we start? 0. So there's my axis. And so as I bring in some Q, I'm starting at this point right here. No heat added. I'm 0 degrees C, liquid. I'm going to eventually get up to 100. And it'll take only, I didn't really draw that too well, 420, right? Less than 500, less than half. Goes like that. As I'm starting to add Q, the temperature goes up, 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 up. Then it hits 100. Does it continue to go up? Does it go flat? Does it go down? What's happening? Flat. It goes flat. And it's got to march out from this point out to the next point, 2,000, what was it, 257. So it's going to go all the way out to 420 plus 2,257. So it goes all the way out to this value of 2677. Try to draw it to scale, staying at 100. Now it's all saturated vapor. As I continue to add heat, then it's even going to be steeper because it's going to travel up to 200 degrees C, and it'll do it, and it'll be 2877. Basically, I've graphically plotted the information that we just talked about. But it really emphasizes there's a lot. What did we say? 77% of the total heat was just devoted to changing phase for this problem. There's another plot that I want to develop because I want to review this parameter, C. C, constant pressure, is by definition from Thermo 1, what is the specific heat defined in Thermo 1 as? Should I pause, walk around? I think somebody said, look, don't come near me. I'm an idiot, right? Is that what you said? You'll go away. You don't like that when you come and I look over your shoulder and say, hey, why do you have a blank sheet of paper? What is the definition of specific heat? Yeah. And so it's the rate of change of enthalpy with respect to temperature holding pressure constant. So why don't we do this? Why don't we take the same data, turn it around, and do temperature on the x-axis, and we'll do enthalpy on the y-axis, because what is the slope of that curve? dH/dt is C, specific heat. So it's the same data, it's just plotted a little different. So let's go ahead and start. What's our temperature maximum going to be? We went from 0 to 1,000 to 2,000, not 2,000, I'm sorry. 0, come on now. 0, then 100, then 200, right? That was our temperature scale. And then what about our enthalpy? What was our maximum? 1,000, 2,000, 3,000. Units kilojoules per kilogram. Okay. So let's plot this starting out here. If I wanted to go up to a temperature of 100 degrees C, basically I had to, it was 420. So 420, 100, there's my line. Make sense? But then I kind of stuck at 100. And as I added energy, H went up, 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 but the temperature didn't go up, 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 up. So it went straight up like this until it got to a value that was, like this, 2677. Way up. Then, as I started to heat its saturated vapor, the temperature go up, up, all the way to 200. It's only going to go up to 2877, and so it's not as steep, but it gets up to 200. What did we say the slope is? The change in enthalpy with respect to temperature? This slope of this line is the C sub P of the vapor. It's about 2. 2 what? Kilojoules per kilogram Kelvin. What is the slope of this line? Yeah, C sub P of the liquid, which is about 4.2 kilojoules per kilogram Kelvin. All right, this finally gets to the point. If you were an engineer and said, I know that this is a straight line that goes straight up, right? It's straight, straight, straight up. But I sure would like to maybe think about having an effective specific heat for water during the phase change. What do you think is the best option for that? Answer A, B, C, or D. Okay, so another word for infinite is huge, very large, big, big. All right, if you wanted to kick this back a skosh, put this as 99.9 degrees C down there, and 100.1 degrees C up here, right? And then it's going to undergo a change in the enthalpy of 2257 kilojoules per kilogram. The slope of that line would be the C sub P in that range would be the change in enthalpy, 2257 kilojoules per kilogram, divided by the temperature change. If I said, really, I'm going to cheat a little bit. I know it's straight up, but I'm going to say it goes from 99.9 to 100.1. That's a 0.2 degrees C or Kelvin temperature change. Take your calculator. Isn't it like multiplying that by 5? Somebody says, okay, great. Let's put it at 99.99, and it goes to 100.01. See what I'm doing? I'm steepening the curve. What's happening to the effective specific heat for the... This is the best answer. Okay, I guess I'm not... The whole idea is we have this heat capacity rate. And when we want a large heat capacity rate, we talked about really turning on the pumps and pushing a lot of mass flow through it. But you know what? How can you get a huge C heat capacity rate near infinity? Think about having an effective specific heat near infinity. Essentially, condensing or boiling, changing phase, gives you a huge heat capacity rate. So for this fluid right here, easier question. Look at the hot profile. This is my hot. Look at the cold profile, temperature profile in this counterflow, whatever, I shouldn't have said that. But anyway, in this concentric tube heat exchanger, which fluid is undergoing phase change if you had to say one of them? Is it the hot? Is it the cold? Or is it, I really still don't know. So this type of heat exchanger is fairly common. What you have is a little inlet, and then it comes out, and then you have a little outlet. And so maybe on the shell side, you bring in some hot fluid that is saturated vapor, and it flows over a tube that runs through the middle that's cold. The saturated vapor, it's going to see a cold surface. What's it going to do on the outside of that tube? Condense and drip off. And then with a little help from gravity, you could collect it and bring it out as saturated liquid. You'd just have a little puddle down here and drain it, slope it a little bit, and you would bring it out. This is very common in heat exchangers. When you have the hot fluid undergoing condensation, it's as if it has a very, very large specific heat. And so it's the hot fluid that's really not changing, because if it's constant pressure, let's say it's 1 atm, it comes in 100 degrees C, saturated vapor. What temperature go out? 100 degrees C, saturated liquid. Okay, so there you go. Let's just grade it. Yeah, okay. Without going to clickers on this last one over here, we have the hot like this, we have the cold like this. Guess what? Both of them. One could be condensing, one could be boiling. The hard question is, in this one, is the hot fluid, which you would think, oh, that's going to evaporate, that's going to, vaporize. No, the hot fluid's one condensing, and the cold fluid's doing the vaporizing. But anyway, I was hoping this would build some great insight as we solve a problem. So we have this problem. Concentric tube heat exchanger, counterflow mode of operation is thin-walled inner 25 millimeter diameter inner tube and an outer diameter outer tube. This piece of information, after you read the problem 2 or 3 times, is a distraction. That's okay. You can handle distractions. But when you were like a freshman, it's like, they want me to solve this problem. They've given me this piece of information, this piece of information, this piece of information. I must need to use all 3 pieces of information. And it really throws them for a loop when one piece of information is just irrelevant. But you could add part D or E later to this problem, and I think we do, but not today, where that outer diameter of the shell is needed, but not for this part A, B, and C. Okay, so we have oil. If you want, we can start collecting some information. And we read about its mass flow rate, specific heat. It comes in at 130 and leaves at 70. Right away we say the temperature of the hot is the oil. Temperature hot in is 130 degrees C. Temperature hot out is 70 degrees C. And you have the heat capacity rate of the hot, which is the product of the 1.9 times 0.1, 0.19 kilowatts per Kelvin. And then the cold fluid is water. And we say the temperature of the cold in is 25 degrees C. The heat capacity rate of the cold is the product of 0.2 and 4.2, 0.84 kilowatts per Kelvin. What's the temperature of the cold out? That's the question, part B, outlet water temperature. That's for part B, so it's not given. You're given an overall heat transfer coefficient. Now, take a look at the units on U. Is it 110 kilowatts per meter squared degree C, or 110 watts? Where am I, when I'm grading exams, where do you think I'm going to look for an error that some student might make? But it's a big difference. We want to avoid factors of 1,000 error. So if you could put it over here, you could put 0.11 kilowatt per meter squared degree C for you. That'll work. Okay. All the information, I believe, is tabulated here. How do I calculate the rate of heat transfer? What is the symbol for part A, and how do I calculate it? Should I pause or just blow through? Blow through. It's Q, and I look at my hot fluid. I have C of the hot. I have the temperature hot in minus temperature hot out. And I crunch numbers, and I find that this is so much. Let me see. 11.4 kilowatts. A lot of people, they'll just put 11.4 and, hey, professor, you fill in the units. No, no, no. Chase your units. Okay. Now, outlet water temperature. You go to the energy balance for the cold fluid, temperature cold out minus temperature cold in. You rewrite it in terms of temperature cold out is equal to temperature cold in plus Q divided by the heat capacity rate of the cold. You substitute numbers, and you find this comes out at 38.6 degrees C, temperature cold out. What is the length of the heat exchanger required? That's sizing the heat exchanger, isn't it? So the length, so the area of the heat exchanger is pi dl. So I'm looking for that L. All right, I need to use this equation. Q is equal to UA LMTD. Where did that equation come from? It's our rate equation for heat exchangers. You just can't willy-nilly push heat across. It's got to be convected out of the fluid, conducted through the solid wall, convected into the other fluid. And so, okay. So you ask yourself, get delta T log, get the temperature difference on one end of that heat exchanger, get the temperature difference on the other end of the heat exchanger, get the log mean temperature difference calculation. You got U, so you find A is equal to Q divided by U log mean temperature difference. And you find that the area required comes in at 1.5824 meters squared, keeping way too many digits. And then you find that the length, unraveling right here, comes in at 20.15 meters. Too many digits, but there you go. Right at 20 meters. See how we did that problem? Look good? All right. There's the solution worked out in detail. Now I need a little bit of time and we'll talk about the effectiveness-NTU method. It's a little harder to get the equations, but a whole lot easier to use. So its use is simple. The derivation is more tedious than the log mean temperature difference method. Okay, so let's just go through it. It's called the effectiveness-NTU method. Well, what's effectiveness? Symbol epsilon, and it's defined as Q, the actual rate of heat transfer occurring in that heat exchanger, divided by some maximum theoretical possible. We'll get to that. Well, what's the other part? It's the NTU. What does that stand for? Number of transfer units. See that? NTU, number transfer units. Okay, maybe that's a little abstract when you first are introduced to it, but it's defined as UA over cap C min. Go slow. Do we understand what cap U is? What is cap U? It's the overall heat transfer coefficient. We worked on that at the beginning of this chapter. It accounts for the convection, the conduction, the convection, what's resisting heat transfer inside the heat exchanger. What is A? The area. You could have a bigger or smaller heat exchanger. Now, cap C, what is that? Heat capacity rate. But then they put this MIN. Minnesota. It's the Minnesota. No. What is the min for? Minimum. So you have two heat capacity rates. You have the hot fluid and you have the cold fluid. You just basically look at them and say, give me the min of them, and that's not that hard. Hey, this is pretty easy. The next thing is you're going to have to calculate the ratio of the heat capacity rates. What do you mean, ratio of the heat capacity rate? Put C min divided by C max. If one was the minimum, then the other was the maximum. Okay, test question. What is the max possible value for C sub R, the ratio of heat capacity rates? Could it be greater than 1? Nope, the max is 1. It goes, the range of C sub R goes from 0 to 1. Okay. Delta T max, you have 4 temperatures. You have the temperature of the hot in, you have the temperature of the hot out, you have the temperature of the cold in, you have the temperature of the cold out. 4 temperatures. Pair them up any which way you want and give me the max delta T. Take this T minus that T. What one would give you the maximum of any pair of all 4 temperatures? That's delta T max. What would it be? Professor, I think it depends on which heat exchanger we're talking about. No. What's the highest of the high temperature? Hot in. What's the lowest of the low temperatures? Temperature cold out or temperature cold in? Cold in. Right. So once you get that down, it's like, hey, that's pretty good. So I got the delta T max. The maximum rate of heat transfer that we need right up in here, now we're able to actually define it. The max heat transfer is C min, the minimum heat capacity rate, times the maximum temperature difference. T hot in minus T cold in. Professor, are you ever going to derive this equations? Yeah, that's the next slide. But let's just see how it's used, the players in the game. So if you wanted to solve for the actual rate of heat transfer, basically you best go up to this equation and you say the Q is equal to the effectiveness times Q max. When you do something like that, you're basically doing what they call rating the heat exchanger. You're saying this heat exchanger is capable, blah, 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 20 kilowatts rate of heat transfer. All right. The other one, though, would be sizing the heat exchanger. Hey, come on. Engineers coined all these terms. What do you think? It's trying to figure out how big A is. How big of a heat exchanger? Do I need to double its size? Triple its size? What size heat exchanger do I need? How would I do that? Well, you'd come up to the, remember, effectiveness is for rating. NTU is for sizing. You look at the definition of NTU. area is going to be the number of transfer units times the minimum heat capacity rate divided by the overall heat transfer coefficient. So there's two methods for analyzing heat exchangers, the log mean temperature difference, the effectiveness-NTU method, and there's really, when you think about it, two main themes when you're analyzing heat exchangers, trying to figure out what is it going to achieve in transferring heat, what is its rate of heat transfer. The other is, how big do I need to make it, size it. Well, without getting into the derivations, there's two key tables. The tables list a bunch of configurations of heat exchangers, and they put them up such that the effectiveness is easily calculated as a function of the transfer unit and CR. That's the general trend. It's like if the effectiveness is a function of the number of transfer units and the ratio of heat capacity rates. Somebody did a lot of work to put these tables together. But once you know how to use them, they're easy, make the job easy. Another set of tables are, hey, maybe I'm given the effectiveness and maybe I'm given C sub R. I need to calculate NTU. This is to size it to find the area. This is to rate it to find or calculate Q. So hopefully you see the pattern. It's like one set of tables to go this direction, the other set of tables to go the other direction. Now I truncated those tables. Or you don't have to have analytic expressions. You can have them plotted. So for this type of heat exchanger, which is described as a shell and tube heat exchanger with one shell and any multiple of 2 tube passes, I know there's long subscripts, but they're being specific what it is. On the x-axis, what do they plot? Number of transfer units. On the y-axis, what do they plot? Effectiveness. And so sometimes you're given the effectiveness and you come over and you find, oh, there's the ratio of C sub R, which is min over max. And then you read off and you find the size by calculating or determining the NTU. Sometimes you're given the size, you come up, you come across, and you rate it. So this is size, this is rate. Makes sense? It's easier graphically, but less accurate because you have to interpolate. So that's the same thing here with a different configuration. There's multiple of these plots in our textbook. There's the derivation you've been waiting for. And I give it to you right at the right time. I saw you starting to nod off, and you just perk awake when we talk about derivations. So I'm telling you, this was brutal. But it's all doable. But it's like, why did they make that assumption and move in that direction with that algebraic manipulation? Because it gets to the right answer. That's all I can say. And so, in the interest of time, I'm just going to say you can work it out. You can work it out for parallel flow, concentric tube, counterflow, concentric tube, and then trust the work of others when they do shell and tube with experimental data and other configurations, cross flow mixed to cross flow unmixed. Okay, but I tried to fit this on one page. I was unsuccessful because I got down here where I have NTU is equal to a function of C sub R and epsilon for that configuration. I continued to do some algebraic manipulation. I compared it with the table and say, voila, I'm so glad I was able to get the same result. Good. Professor, I'm glad you did that. Because as a student, I don't want to do that. I'm reading your mind. And then you do this. You say, okay, well, let's take this equation and flip it around. Let's get the other side to be epsilon, the effectiveness. And so you are really good at algebra. And lo and behold, you get this, and you come down here and say, same. It can be done. It's just a lot of work. Okay? Nobody's ever been tested in this class. Like, okay, start from scratch as if nobody's ever done it before, and you derive the effectiveness-NTU relationships for a concentric tube counterflow. No. It's in the book. We can take the exact same problem that you just solved. Now let's not solve it with the log mean temperature difference. Let's solve it with the effectiveness-NTU method. Same problem. Glad you had good notes, right? So last time we left off, we had the heat capacity rate of the cold fluid was 0.84 kilowatts per Kelvin. The heat capacity rate of the hot fluid was 0.19 kilowatts per Kelvin. We had that, well, first of all, for part A and part B, it was just energy balances. We didn't even use anything associated with a rate equation. It's only part C that you use either the log mean temperature difference or the effectiveness-NTU method. So let's just remind ourselves of the answers for part A, that the rate of heat transfer was 11.4 kilowatts, and the temperature of the cold out was 38.6 degrees C. Now, somebody says, I want you to calculate the length of that heat exchanger. Question, are you trying to size it or rate it? Size it. You would like to get NTU. So you probably can calculate effectiveness and CR, the ratio of heat capacity rates. Okay. Of these two, one is really easy for us to calculate at this point in a study. CR. CR is going to be the minimum, and so which is the minimum? Take a look. If you've been challenged all day, this is your chance to shine. You can get this answer correct. C min is 0.19 kilowatts per Kelvin, and C max is 0.84 kilowatts per Kelvin. So CR is the minimum over the maximum or the reciprocal? 0.19 divided by 0.84 or 0.84 divided by 0.19. It's always between 0 and 1. So there it is. So this CR comes in at 0.2262. Okay, now I need to get the effectiveness. How do I get the effectiveness? Isn't effectiveness equal to actual rate of heat transfer divided by Q max? So I know half of the equation. I know the actual rate of heat transfer, 11.4 kilowatts. I need to get that maximum. So Q max. Should I pause and let you do it or just blow through it? Pause, raise your hand. Blow through it. Man, blow through it. You guys are anxious to get the answer. All right, it's C min times temperature hot in minus temperature cold in. That's our maximum delta T. So our minimum heat capacity rate was 0.19 kilowatts per Kelvin. The hot in temperature is, I'm looking for it right now, 130, thank you. And our cold in, 25. So that's Kelvin temperature difference. So that's 105 times 0.19, and you get 19.95 kilowatts. Now we can get effectiveness. It's the 11.4 divided by 19.95. The effectiveness comes in at 0.5714, blah, blah, blah. Very good, thank you. So now that I have the effectiveness, I can either look for the right equation to calculate the number of transfer units, or I can look at the plot. So this one was a concentric thin-walled. It's so counterflow right here. We would either, if the C sub R is equal to 1, use this relationship. Is our C sub R? No, so we use this relationship right here. So calculated effectiveness, calculated the C sub R, you then use this equation to calculate the number of transfer units. So right here is that same equation. So when we calculate it, we calculate the number of transfer units would be 0.91611. Unravel it to calculate UA or calculate A right away, 1.58. And then calculate L. What was the L from the other method? The same L. The path looks a whole lot different. The results are exactly the same. In summary, we covered the two big effectiveness NTU and log mean temperature differences. Okay? Solve a lot of problems and it'll become clearer. This is the preferred method in practice. Why this method often forces you to iterate. And the other method often avoids the need to iterate. So that's why. Next time I'll talk a little bit more about heat exchangers, but then I think I'll move into a review for the exam, which will be next week, Thursday. Thank you very much for your attention. I'll be in my office if you have any questions for me.